So Subh Khair everybody. We were talking about the Green's function, and last time we kind of set the tone by formally writing it down, and the way I developed the Green's function was I used the method of variation of parameters, and I told you that Green's function is written for an inhomogeneous differential equation. So because the two methods that you have learned so far, one I just talked about briefly was the method of undetermined coefficients, and the other was the method of variation of parameters. And the good thing about the variation of parameters is that you can use any kind of input, but you need to know the associated homogeneous part. So one thing I would like to say again, that you realize that when you have a non-homogeneous part or the input, then you have the total response. One is the complementary function, which is the natural response, plus the response to the input, or the forcing function, whatever you want to say. So the constants of integration, which are to be determined either by the boundary value conditions or by the initial value problem, they are to be determined, or the C's are to be determined from them, but in fact they have no bearing on the forcing term. So forcing term is something which is independent of those conditions. So the Green's function that you constructed was also independent of that, right? So these are the things we need to, and this is, by the way, the same thing that we did when we were trying to solve a problem using the method of variation of parameters, because you knew the solutions of the associated homogeneous part. So if you want to, remove the arbitrariness, you can use the initial value problem or the boundary value problem to determine the C's. But as far as the forcing function solution is concerned, that is independent of that. And that was the same in method of undetermined coefficients as well. That was more obvious because you were constructing the particular solution part by the input. Like if you have a sinusoidal thing, you will write a cos 2t plus b sin 2t, so to say. Or if you have a polynomial, you will write ax square plus bx plus p, and what is to be determined is a, b and c, not from the initial boundary value but from the differential equation itself, comparing the coefficients, and you get the answer. So that is something that we should not have any ambiguity about. And now today I need to be more methodical, because there is something that I'll keep referring to, so I'll write it down. So this is the differential equation that we have. Subject to this, and we said that this can be expressed, the solution of this problem can be expressed as, so let's call this 1. So let's, okay, 1, all right. So y double dash plus p of x, y dash plus q of x, y is equal to 0, y of x naught is equal to y naught, y dash of x naught is equal to y naught. And then the other thing, so it can be expressed as this, which is the homogeneous part, and the inhomogeneous part with the conditions y x naught is equal to 0 and y dash of x naught is equal to 0. So this is the claim, that if you have an inhomogeneous or non-homogeneous second order linear differential equation subject to the initial values, So first we begin by talking about the initial value problem. And we said it can be expressed like this. So because it has to be used, so I'll write it down. And then using the method of variation of parameters, we wrote down the Green's function, we constructed the Green's function, and we found out that the Green's function does not depend upon the forcing function. It depends on the associated homogeneous part. So if you change the forcing function, that does not affect the Green's function. But that does change the total response of the system, because the total response of the system comprises of the complementary part and the particular part. All right, so g of xt that we wrote down was this. So instead of writing again and again, I will just make use, because I have to make use of this. So because in Pakistani universities, this topic is generally not explored in detail and relatively, poorly discussed. So I thought that maybe a couple of examples will also help you understand. So the examples that we did last time were in the context of an initial value problem and just to construct the YP. Okay. So now let's say you have a differential equation. So the question is, solve the initial value problem y double dash plus 4y is equal to x subject to y of 0 is equal to 0 and y dash of 0 is equal to 0. And here I will also write down, so I think I should write it down here also, that y of p that we wrote down was x naught to x g of xt f of t dt. So that is how we wrote down the particular solution for the non-homogeneous problem. So now you have this problem. So go ahead and tell me. So it should comprise of two parts, this and this, where your yp is given by this, and immediately you can recognize that over here the x naught is 0. So I can write that my yp is equal to 0 to x. Now all that I need to do is to solve the associated homogeneous part to write down this g of xt and replace this input function by t dt. Okay. Yc. So this will become m square plus 4 is equal to 0. M square is equal to minus 4. So m is equal to plus minus 2 iota. So which means your yc is equal to c1 cosine of 2x plus c2 sine of 2x. Now if you plug in these initial conditions, so what do we get? आप बताएंगे please? Can you please tell me? क्या नहीं? फौरन नहीं. Just listen. This is yc. These are the two conditions. This includes y dash. It means you have to take the derivative of this once. Now apply these conditions and tell me what are the c's that you find. C1 and C2 की value. You find it out and tell me. Go ahead. The idea of monologue is not a good idea because the sense of participation is gone then. So if you do something, you feel that you are part of it, it keeps you awake also. So can you just tell me the values of C's without actually, calculating everything? So mind maths is also very important when you do it again and again, So I can see straight away that sine 0 will be 0, this 0 will be 0, and I will have C1 is equal to 0. And similarly, when I take the derivative, C2 turns out to be 0 as well. So YC will be 0, right? Now tell me what about YP? Go ahead and tell me. You know what so this is from here, y1 is equal to cosine of 2x, y2 is equal to sine of 2x. Okay. So now construct the G and tell me what the answer is. कोई पेन नहीं है, G of xt लिखें. Okay, good. So if I look at, so let's construct G of xt. It's already given, so you just don't have to do anything. So y1 of t would be cos of 2t, then y2 of x sine 2x minus y1 of x, which is cos 2x and sine 2t, divided by w, and w is what? y1, y2 prime. Yeah. So it will be W of t, just have a look at your notes. What did we write when we wrote down the W? So it was W of t. So it will be cos 2t, and I will have a 2 here, and I will have cos 2t. Yeah. And minus, well, by minus eventually it will, so I'll start with minus, and then I will have 2, and I will have, but this will be plus. So it will be sine square 2t, so you will have, so it means W of t is equal to 2. Okay? So G of xt will be 1 by 2. Now if you look at this, can you tell me? Can we write like this? Well, let's say x minus t. Sine 2x cosine of 2t, sine 2x cosine of 2t minus cos of 2t, well, what is it? Sine of a minus b is sine a cos b minus cos a sine b. So go ahead. So this will be cosine of 2x sine of 2t. That's what it is. Okay. All right. So now straight away we can go here and write that my yp is equal to 1 by 2 0 to x. This whole thing, which is sine of 2 x minus t t dt. Now solve it. What is a better way of solving it, Laiba? Should we try and solve it like this, or should we write this so that I can take the x out and I write t cos of 2t and t sine of 2t? No, it is integrated over t. X is the, yeah, so you just, it is being integrated over t, not over x. So you can take it out. So you drag it out. So what you will have is a t cosine of 2t and a t sine of 2t, and then you will do the integration by parts. And so anybody would like to do that and convince him or herself that the answer would be yp of x is equal to 1 by 4x minus 1 by 8 sine 2x. That should be the answer to this problem. The best way is that you don't write it like this, but instead use this independently, so that you drag the x's out, and t cosine of t 2t you will solve using integration by parts, and you will solve t sine of 2t using the integration by parts. Would you like to do one part just to, so one part should be done by 3-4 people and the other part should be done by the 2 people, so that you could, you at least you understand that although it's very trivial, this is integration by parts that you have done umpteen times before. So okay, I mean, maybe we can just skip this, and this is what it is. So last time we just talked about constructing a particular solution to the problem, but now we have taken an example where we have to construct the whole solution. So what we have found out, that the complementary part turns out to be 0 and the particular part turns out to be this. So the whole solution will be this, subject to these initial conditions. You know that if you change the initial conditions, you will change the answer because the C's would be different, right? All right, okay. So you already know that y is equal to yc plus yp is the solution of a second order non-homogeneous differential equation, right? But over here, these are the conditions that you have. You know that yc is the solution of the natural response, and yp is response due to the forcing term. So the question is, can we show that we can retrieve these conditions using the solution y is equal to yc plus yp? So that's so in both cases, both for the boundary value problem and the initial value problem, this is something that you need to convince yourself that once you write it down, because it was the claim that if you have this kind of an equation, the answer would comprise of this and this, right? So now you have to see that if this is the response, can I get these conditions once I write something down for this particular problem? Questions here? Any problem here? Please ask. Okay, if this is clear, then let's go for it. This is something that I'm not going to remove, because so these are the things that I would like to have, because repeatedly we are going to use them. All right. So now comes this. Okay. So what do you have? You have y of x is y naught and y dash of x naught is, okay. So once you say that your solution is y is equal to yc plus yp, then you will write y of x naught is equal to yc of x naught plus yp of x naught, and y dash of x naught, that will be equal to y dash c of x naught plus y dash p of x naught. Okay? So now tell me, what is it that you get when you plug in the values? So this implies that y of x naught is y naught, because yc of x naught is y naught. You see, this is the solution of the homogeneous part and subject to these conditions. And now you are actually applying them and see whether the claim is right that you can split the whole solution into two parts. So once you do this, you get this. Now plug this value in. Y dash of c x naught is y1. So y dash of x naught is equal to y1, because so you can do it both ways. You can write it down and you can say that these ought to be the conditions. In fact, I should write 2 here and 3 here. So these are the conditions that fit the bill. I split this one with this is now essentially, when I write this problem as this problem, so when I find the solution, what does it mean? What is the difference between? Are you okay with the English language? I hope. So you can answer in Urdu, that's not a problem. So if this is the differential equation and I write this down, so essentially the solution of it will be what? Natural response, which is represented by yc. But we said that the problem would be such that for the homogeneous part, yx naught will be y naught and y dash of x naught will be y1. And for the non-homogeneous part, the conditions, the initial value problem would be this. Initial conditions would be these. So now you just plug them in the y is equal to yc plus yp, and you see that this is exactly what it is. In order for this to satisfy this problem, my splitting up of the problem ought to be like this with these initial conditions. Otherwise, it will not be satisfied. So I hope now I've managed to convince you that this is the right way to write down the initial values and splitting the system into the natural response and the particular response. Make sense? All clear? Good. Okay, so now he writes. So he wants us to solve this problem. So what he does is that he doesn't change the homogeneous part, but just change the he changes the input, and the conditions are y0 is equal to 1 and y dash 0 is equal to -2. जी.
इसका मतलब ये है कि जो होमोजेनियस पार्ट है, नॉन होमोजेनियस पार्ट जो है, उसका सॉल्यूशन जो है वो बाउंड्री पर वैनिश करेगा और उसका डेरिवेटिव भी वैनिश करेगा.
जी जी जी, मतलब आपकी कहानी बिल्कुल एग्जैक्टली. या That is what it is. So otherwise, y is equal to yc plus yp won't be the solution. So it means that there is a method in the madness. When we wrote it down initially, per se you don't understand why this condition is imposed. But the moment you try and write it down like this, which you have already proved, that this ought to be the solution of the second order non-homogeneous differential equation, it turns out that this is the demand, that if you want to say that these conditions are right, then this ought to be true. Otherwise, you won't be able to write it down as a function of two, I mean the complementary part and the particular response part. Yes, go ahead.
जो इलेक्ट्रोडायनेमिक में हम सोर्स की बात करते हैं
जी जी
तो वो भी हम कहते हैं कि बाउंड्री पर ये वेनिश करेगा ये इस वजह से बाउंड्री पर मतलब वो चार्ज जो है वो जीरो हो जाएगा.
That is general. So, for instance, if you have an open system and you are looking at a response of a system of any charge, of any force, so if you go away from the source, what do you expect? Yeah. So that's a natural, intuitive, expectation that when you go far away from the source, unless the source remains. So let me give you an example. The solar wind comes from the sun. So people have observed that solar wind accelerates to very long distances. But the thing is, if the origin of the solar wind is sun, so why does the solar wind accelerate when you are so far away from the sun? The answer is that it's not the source at the sun which is now responsible, but in fact there are so many other wave particle interactions which are giving rise to so many acceleration mechanisms, for which solar wind accelerates and it terminates at the termination shock to many AUs. Probably it's I guess 1000 AU where it's the termination point. So this is the point. Similarly, the universe expands. There was a big bang and it's still expanding. So the question is, why is it still expanding? So naturally speaking, once you go away from the source, your intuitive, I would say expectation is for something to die off. If it doesn't, it means there are now some sources present. Let me give you another example. Because I am a plasma physicist, I can give you an example. So this is, the solar wind comes and it's a magnetized planet, a bow shock is formed, so let's forget about that. So what we see is that generally the distribution is Maxwellian here, but it becomes suddenly flat topped, electron velocity distribution becomes flat topped here. Now, in principle, if something happens here and this flat top is formed, after some time, what you expect is that you should again get a Maxwellian. But repeatedly you see these flat top distributions, so it means there is a source present all the time which keeps feeding it, right? So this problem is like not that simple, because you need to understand the mechanisms that are responsible for continuous acceleration. Otherwise, away from the source, everything is expected to die off and die out. Okay, so you can find the solution to it as well. But the only thing that he says, and I would like to share it with you, is that sometimes, let's say you write it down like this, and you have some cosine of 2t here, or 2x, let's say here. And in yp, you also get some 3 or minus 3 cosine of 2x. So if you write like this, or maybe I can write some x here as well. So I will have 1 minus 3x cosine of 2x and so on and so forth. So what he says is that by adding similar terms, the only downside is that then you can't see clearly what is the response to what is the natural response and what is the system's response to an input. So if you write something like this and don't add, then you can clearly separate the two. When once you add and show it to someone, then of course you won't be able to say that this is the solution to the natural response, and that other is the response to the forcing input, a forcing function. So that is something which is instructive. All right. So now we come to So there is another problem which is very good. Piecewise functions you're familiar with? Okay. So the problem is, so it's the same problem that he has given before, but this is now the arbitrary thing. Solve the initial value problem. Y double dash plus 4y is equal to f of x, y of 0 is equal to 1, y dash 0 is equal to minus 2, and the forcing function that you have now is defined like this. It is 0 for x less than 0. It is sine of 2x for x greater than or equal to 0 and less than or equal to 2 pi, and it is 0 for x greater than 2 pi. So I'm not going to get into the details of solving this problem, but only to tell that how I'm going to deal with this when I'm going to write down my solution. So solution, of course, is this. And what is x naught here? 0. So I will have 0 to x, whatever gxt, which I know I can construct because I can solve this homogeneous part in a jiffy. And now I have f of t dt, for which I have to apply these conditions. Okay? So let's say the first part that you do would be what? X less than 0, right? So for x less than 0, what will you do? It will be 0, right? Now look at this. This is, so let's say if you say 0 to 2 pi, so I will ask somebody now, let's say, whom should I ask? Okay. So once you see 0 to 2 pi, then how would you interpret it? Can I say this is x greater than 0 and less than 2 pi? Or less than or equal to 2 pi? Do you agree? Yeah.
Sir, actually, yes, we can.
So x greater than or equal to 0 and less than or equal to 2 pi. So now I can plug in sine of 2t and solve it. Okay. Now comes the final thing. We have just convinced ourselves that this is x greater than or equal to 0 and x less than or equal to 2 pi. So what about x greater than 2 pi? 0. No, how do you write it down? Any idea? Good. So I should write 0 to, can I write like this? Should I write like this and this? Yeah? So once you write this, what does it mean? Greater than? Because this is greater than 2 pi. So this part will be 0 and you will just do this and solve it. Okay? Because this is the only tricky part, because this has to be, that is why I wanted to do it, that you have, now you know how to deal with an initial value problem when you are given a forcing function which is a piecewise function. Okay? Meaning it acts differently in different regions. right, good. And now is the time to talk about, so I'm done with the Green's function vis-a-vis the initial value problem. So now I have to apply the Green's function to the boundary value problem. Okay. Up till here, if there are any questions, please ask. I hope there are a couple of questions that might have come to your mind. Okay, then we begin. And I'll remind you about the boundary conditions, and then we will talk about the rest. It's a matter of integration. No matter what the response is, you have to just integrate the problem. Nothing new will pop out, whether you take the delta function or any function. It's just the integration g of xt multiplied by the f of t dt. Yeah. आपको प्रवेश सर ने लास्ट टाइम बताया भी था कि वो x अगर डेल्टा x माइनस x प्राइम f of x, so it will be equal to f of x prime. So even in plasma, when we start with the Dirac delta function because that's the easiest one to integrate. Because if you take the bi-Maxwellian and Maxwellian, they are the Gaussian functions, so aren't easy to handle. You have to deal with so many other things, but Dirac delta function doesn't have that kind of problem. But it is a distribution function. That is the important thing. I hope that you understand that Dirac delta function is kind of a misnomer because something that exists only at one point and it becomes zero at every other point, it's not a well-behaved thing. That is why it is a distribution function. So it is like this basically. So it is a distribution function. And that is why in standard plasma physics books, you start with taking the distribution function as a Dirac delta function, which is a distribution function. All right. No more plasma physics. Boundary value problem. So boundary value means that it is defined over an interval. Unlike the initial value problem, you do not have x naught only. Now you will have an a and you will have a b. You will talk about this interval, and of course you will give conditions. Okay. So what are those conditions that I wrote down the other day? A1 y of a plus b1 y dash of a is equal to 0, a2 y of b plus b2 y dash of b is equal to 0. All right. A1, b1, a2 and b2, these are the constants. Now what is the goal here? The goal here is again to find a particular solution, the kind of solution that we wrote down for the initial value problem, but over there we had just one point, and now my conditions are not these. My conditions are these. So I have to now actually do something about it, and whatever I do ought to satisfy the boundary condition, the general boundary conditions for a second order linear differential equation. Okay? So what we do now is we say y double dash plus p of x y of dash plus q of x, y is equal to 0, and that is not enough, subjected to a1y of a plus a2y dash of a is equal to 0, a2y of b plus a2y dash of b is equal to 0. And they ought to be continuous over the interval AB. Not that these things ought to be continuous over the interval AB, this should also hold over the interval AB. That is the prerequisite for any solution to be a legitimate solution here. Okay? Any questions? Tell me, otherwise I'll go on and write down. So the rest stays the same. It's only this thing that now you have not x naught to x, but you have a to b. These are the two conditions that need to be satisfied. Ji? These are general second order differential equation boundary conditions. So it contains all the conditions that you can have. You can put this equal to 0, put this equal to 0, so it means you are defining function at a point and slope at another point. You can take this to be 0, you can define the slope at point A, you can take this to be 0, you can point the function at point B. So these are all the possible combinations that you can have, right? So we talked about it when we were talking about, although I rushed through it, but yeah, so good. Yeah, makes sense. These are the different ways that you can, and why do we do that? You have two constants to be determined. So those two constants will be determined from the two conditions that you will give. So in every case, you will put 2, 0. Either A1 or A2 would be 0, or, this ought to be B1 and B2. Yeah, so either this one is 0 and this one is 0, and so on and so forth. There are many combinations that you can try, but the idea is to find the constant of integration.
The question is this: for arbitrary A1, A2, B1, B2, this will not have a solution. This then amounts to 4 conditions, not one.
Yeah, so these are all, this is a general condition.
Yeah, but then if it's so general, that solution, that differential equation may not have a solution.
Just a moment. The thing is, the moment you define that y of A is equal to, let's say, x naught, y naught, sorry, and y dash of B is equal to y1. So now what do I need to do? I need to put this equal to 0, I need to put this equal to 0 so that I'll.
But when you write it that way, you give the impression as though there are 4 arbitrary constants. If A1, A2, B1, B2 are
Okay, just a moment. The question is, how do you write all the possible combinations that are available to get two conditions? That was the goal. So this is the only way. So tell me, if you want to say, I'm going to define a function at a point and a slope at another point, how will I write that? Over here I can't write that.
Yeah. Then in the theory of differential equations,
Yep.
you have to prove that there are only 2 conditions that you can impose.
Yes.
Not 4.
So these are not 4 conditions. These are the possible combinations. Yeah.
The rigorous theory of differential equations requires you to prove
Yeah.
that there are 2 and only 2 points, or are there 3, or are there 4? That's a non-trivial issue that has to be addressed when you do the theory of differential equations, not how you get the solutions, but the theory of differential.
Yeah, but if you are defining defining an interval, so the interval is defined at 2 points. Now the thing is, what are the conditions that you can give at those 2 points? It is not to prove that these are the 4 points. It is just to write in a general way the different combinations.
When you say the derivative is something,
Yeah.
you're not actually giving one number.
Yeah.
You're acting in one point on the trajectory, you're giving 2, because a derivative is
Is of a function. Yeah, sure. Yeah, right.
so there is some proof that is now needed here.
Okay. Yeah, I understand your point that if you are saying that you know the derivative of something, it means there is some function out there which is continuous, differentiable, and that is why you write down the differential. But the purpose of writing this is that from these conditions you can have all possible combinations. Because in principle you can never get this. You're always going to get this. You will be given this. But the thing is how to write it down. So one thing is that you don't write it down. But yeah, I mean, I'll have a look. But you see, when he writes down, the Zill writes it down.
There's the Dirichlet and the Neumann.
Oh yeah. So that is also something that you define. So you have said it. So you define function at one point, and again the function at the same point. This is one. When you have this kind of a thing, this is a Neumann condition, a Robin condition, as we say, that you give a function at one point and a derivative. How do you get it? That is besides the point. You talk about the given. So if you are given this and you have to solve a differential equation,
Given impossible conditions,
then my solution will tell me. I have shown them
you will
that I chose a boundary condition.
and you will not find it.
Yes, so I wrote.
That's why you need the theory of differential equations.
Sure. But the boundary condition, if you choose a nonsensical boundary condition, when you plug it back, those boundary conditions will be not satisfied by the solution, and that's why I did the problem. A boundary value can have infinite many solutions, it can have a unique solution, and it can have no solution at all, provided you choose the wrong boundary condition. Yeah, so I am allowed to do that as long as my solution is satisfied by those boundary conditions. Otherwise, I can come up with the fact that these are erroneous boundary conditions.
I don't know what erroneous means.
Yeah, so
Okay, but let's go.
for instance, y pi of 2 is equal to minus 1. I did a problem. The solution was y is equal to c1 cosine of 2t plus c2 sine of 2t, and this led them to this thing, which was nonsensical. So if I say this is the solution and I apply these boundary conditions, immediately I know that this is nonsensical.
Condition will not have an explicit solution. Therefore, you need a theory which tells you at how many different points can I specify that y is this, that,
Yeah, sure.
and can I do it at 25 different points? No, I can't. But why? That has to be established by use of appropriate theory. And but let's go.
Yeah, okay. But of course, as I pointed out earlier, in the theory of differential equations, in the theory of nth order differential equations, it ought to be guaranteed that these are continuous differentiable functions. If they are not, you can't apply the theory. But this thing proves that the boundary conditions. So, in fact, these boundary conditions are not to show you that you need 4 conditions. Okay. So maybe we will talk about after the lecture. But yeah.
So provided that we have 2 conditions, y of a is
Yeah.
and y prime.
These are given to get 2 conditions out of it. So always and always throughout Zill's book, whenever you write down these boundary conditions, I will assume let's put b1 equal to 0 or a2 is equal to 0 so that I get 2 conditions, because I know that I am doing a second order differential equation and I need 2 conditions.
But sir, these conditions should satisfy those equations.
Mhm.
2 equations.
Yeah.
So if
So they satisfy those conditions when I say that A2 is equal to 0 and B1 is equal to 0.
So then why not has to be 0? Because we have
Pardon
0
me?
on the right hand side.
Sorry?
Sir, then why not has to be 0? Because we have 0 on the right hand side in equation number 1.
Yeah, so okay, yeah, so you have to do something to show that they do not have to be homogeneous always, right?
So then there should be some.
Yeah, so you can have then something over here. Let me so I can prove you. So I intend to prove it to you that this is the problem. These are the two boundary conditions, and I'll prove to you that once we plug it in there, y is equal to yc plus yp gets satisfied. Okay, because once we satisfy this, then we have proved it. All right. Gigi, please.
So you said that when we are doing the conditions, then we need to put like A2 or B1 equals to 0. But I think we don't have to do that because we know that A2 or B1 can be arbitrary, and if the given conditions are not homogeneous, then they have to do something.
Yeah, okay, yeah, that's another way of saying it, but in that case, you are talking about four conditions, right? This is what Pravesa was mentioning. That once you say that this is non-zero, this is non-zero, everything is non-zero, then basically what you are saying is ya, y dash of a, y of b, y dash of b, so you are giving four conditions then. Okay?
But that can be possible. For example,
But for a second order differential equation, you ought to give two conditions, right? So let's do it. Let's do it, and then we will come back to this problem, and we are going to show that this fits the bill. Just like we showed that these conditions can be obtained from the y is equal to yc plus yp I wrote. Okay. Okay. All right. So the only thing that gets changed over here is that I will write down, using the method of addition of parameters, I will write my u1x to be minus b2x y2 of t f of t over w of t dt, and I will write my u2 to be u2 of x to be, this will be a2x y1 of t f of t over w of t. This is not something that we are not doing anything new. This is the same variation of parameters method. The only difference now is that you are not starting from x naught to x. Now you are having two things. You will have b to x and you have a to x. Okay. So it means whatever you are writing, you need to prove that these things are continuous. Okay. So your g of xt now is defined in a piecewise manner, right? Because there is this part, and of course when you write it, because what is the solution? u1 of xy1 plus u2 of xy2. So you will have these two as the solutions, but you need to write down now, because the Green's function still says the same, but now you will have to write down your g of xt, and let me write down g of xt here. So what will be g of xt? If I just change it, so I can write this as x2, oh b, sorry. So my variable t would be what? So if I write g of xt, which is equal to y2, well, let's first write this one. So I can write this like this as well. I can write this as a to x something plus x to b something. Yeah. So I have t greater than and equal to a less than and equal to x, and I have t greater than and equal to x and less than and equal to b, and this part will be y1 of t, y2 of x by w of t, and this part will be y1 of x, y2 of t divided by w of t. Okay? ठीक है जी? And if you are wondering where this has come from and this has come from, because this has come from here, because these y1s and y2s, because they do not depend on t, they will go inside. Clear? Did you get it? Because I have written this, but this is just u1, so you have to multiply it with y1, so that is why you will see a y2 of x here and a y1 of x here. And these are, so now my Green's function is defined piecewise for the boundary value problem. GG, of course, yeah. But it is not written in that manner. For the initial value problem, you could add the two and it could be defined like this. But now you have to define for each individual integration